So precipitation comes in various forms, and I am guilty of interchanging rainfall and precipitation because my research is mostly focusing on the rainfall component for Australia. Apologies to anyone from any part of the world where snow is a pretty big deal. Nevertheless, we get these different forms of precipitation: rainfall, snow, sleet and hail, where sleet is really a hybrid of snow and hail. And how they form really is a function of how quickly the warm, moist air is risen and the processes resulting in that fast lifting that leads to these different forms of precipitation. But all you really need to understand, I think, for this lecture is that it's because the air is reduced, the temperature of the air is reduced to a point where that air can no longer hold the moisture and it forms precipitation. So rainfall categories based on how quickly the air is lifted, just describe that. But we have frontal rainfall. That's when those low pressure systems, low fronts, cold, moist air encountering warm fronts. We also have the lifting that's due to terrain elevation. Flow of air over a mountain leads to lifting of the air above it, and that's what we call orographic rainfall. And then there's the rain that's a result of the strong convective heating of the Earth's surface. We see this typically more commonly in the tropics, where there is an intense equatorial low as a result of the intense solar radiation heating in the region. So frontal rain. That's when rain forms at the boundaries of a cold and warm air mass. So that cold air mass comes in, lifts the warm air mass above it. And because that's often quite a steep ascent of that warm air into areas of the atmosphere colder, with less pressure, the clouds form quickly. The clouds typically resulting from this are cumulonimbus, but you can also get stratus clouds as well. But the cloud classifications I won't go into in this lecture, but it's a whole area of physics in itself for how these clouds form. But for your purposes, frontal rain, one example is when a cold air mass meets a warm air mass and lifts that warm air into areas of the atmosphere that are colder with less pressure. The other type of frontal rain results from cold air mass being overtaken by a warm air mass, if you like. The warm air mass catches up to a cold air mass. That warm air mass rises above that cold air mass, leading to precipitation. Now, this is typically a more gradual lifting, and so the clouds that sort of form out of this process are longer, are thinner. These are the stratiform clouds, or the white puffy cumulus clouds that we see on a nice day in Australia. Orographic rain is a result of air flowing over mountains or hills. What we have is air encountering a physical barrier in the form of a mountain range. The windward side, so that's the side facing the direction of airflow, the air in that area is lifted, and as that air lifts to rise above the mountain, it goes into an area of atmosphere of less pressure, and that is cooler, leading to the precipitation or the condensation effects we know. But as the cloud lifts and turns into precipitation, what we see is rain falling on the windward side of the mountain. And as the airflow continues over the mountain and down the leeward side, the side facing the opposite direction to the wind, you see there's no rain because pretty much exhausted its supply on the windward side. So what that ends up happening is that on the leeward side of mountains, you see a rain shadow. It's an area where you get less rain than you would on the other side. And Australia has a very prominent Great Dividing Range on the east coast of Australia. often you'll see this idea of a rain shadow, moist air coming off the ocean, encountering the continental dry air mass. You see the rain on the coast, but not so much inland. Another nice example of orographic rain is in Tasmania. Anyone who knows the geography of Tasmania knows that there is a plateau here. I forget what it's called, but it's quite a large mountain range on the west coast of Tasmania. Air flows are typically from the west, that moisture-laden air rising above the range on the west coast of Tasmania, on the leeward side, resulting in a lot of rain, and not so much on the leeward side. Forgive me if I said this was the leeward side. This is actually the windward side. This is the leeward side. So if you look at the number of days where you're getting more than 5 millimeters in a year, generally, this is the area where Tasmania cops most of its rainfall. Finally, we have the convective rain. So convective rain is a result of strong surface heating, that air lifting, and the kind of the circulation patterns that we saw in the previous, the first lecture this week, leading to these circulation patterns where that lifting air, creating a low pressure, and air flowing in, converging in the base, and lifting the air mass. As the air lifts, it encounters cooler environment, less pressure, so strong condensation, and forming these cumulus clouds. Now, typically cumulus clouds can form up here. These are sort of called the fine weather clouds. If you see these in the sky, it's typically a nice day. There's localized convection leading to the formation of these clouds. When there's sufficient energy, a sufficient amount of moisture in the atmosphere, the lifting is strong, they form the cumulonimbus clouds. And these are the thunder clouds, the clouds that lead to severe storms, including hail damage. And we saw many examples earlier this year of convective storms, one in particular shutting down the university for all the hail damage it caused. Now, they're short-lived, but they're quite intense because of that localized convective heating. Broadly across Australia, convective rain dominates the northern part of Australia. So northern part of Australia, as you recall, gets its rain in the monsoon season mostly, where you can get up to 3 meters of rainfall on average over the year. And the number of days where you get thunderstorm activity. So thunderstorms are typical of those cumulonimbus clouds, those strong convective rainfall events. Yeah, you see a lot that dominates the landscape in northern Australia. Convective rain resulting in large volumes of rain falling because of that moist air mass being transported through the monsoon, and because of the strong surface heating in our summer, the monsoon season, we get a lot of convective rain in northern Australia. But the beauty is that we've got a large country surrounded by sea. So for any given day, you can see various forms of rainfall from the localized patchy convective systems you see, like these dots, through these large bands of rainfall, the more frontal rain or convective rain, stratiform rain. So convective, localized, or you've got the frontal or stratiform, more elongated features in the rainfall across the country. So to summarize that bit, we have frontal rain. It's more widespread. It's typically mild to moderate in intensity, can be occasionally heavy or long lasting, but it is typically long lasting. It's more common further south in Australia, or just across the world, more the higher latitudes, further away from the equator. And because they're frontal, and you'll recall from our last lecture, pressure systems in the larger latitudes, the higher latitudes, or further south, pressure systems tend to persist, forming these stratiform clouds that are more predictable because they follow the pressure patterns that stick around a lot longer in the higher latitudes. Convective rain, however, is a bit more localized. That can be moderate to heavy and often extreme. And there's a lot of energy dissipating in a very short amount of time. They're typically short-lived and they can pop up anywhere. As long as you've got enough heating and moisture in the air. We find them more commonly in the tropics. In our case, we find across Northern Australia, particularly in the monsoon season, the December, January, February months. And because they're happening in the tropics, they're closer to the equator where Coriolis breaks down. So we don't have those nice circulating patterns of high to low pressure. Instead, what we have is the equalization of winds being more direct. As a result, they're less predictable. Finally, there's orographic rain, where the windward side of a mountain gets more rain than the leeward side in what's called the rain shadow, because all that moisture has been dissipated on the windward side. As you know by now, air movement in response to the differences in atmospheric pressure lead to wind. And so it's the equalization of pressure between high and low that makes a parcel of air move from high to low. But because we live in a rotating Earth, there is the influence of Coriolis. So the flow is out of a high pressure cell counterclockwise, deflection to the left, out of a high, and clockwise into a low pressure system, or clockwise, or deflecting to the right into the low. And it's the opposite in the Northern Hemisphere. So when we look at a synoptic chart, these are the typical charts you'll get from the Weather Bureau describing the mean sea level pressure on any given day. They're made various times a day. I think 4 times a day, every 6 hours, you'll get what's called a mean sea level pressure analysis. That's the best estimate of the distribution of pressure, surface pressure across the globe, but in our case, the region. So here's an example for this is a forecast made at 1800 hours UTC. So that's around about 4 o'clock in the morning, 24th of July, 2013. What we have here is a large pressure, high pressure cell. Remember, the flow is counterclockwise out of the high and clockwise into the low. So we have the continental dry air mass. We have a frontal system being driven by winds, those circular patterns of airflow from high to low, pushing this cold front on moisture laden, I might add, because it's over the ocean, onto the dry, warmer air mass of the continent. And this is how we delineate the cold front. So not surprising when you look at the rainfall in the area. There was some rain over southwest Western Australia as a result of the cold front, moisture rich, colder air encountering the warmer air from the continent. So it's the movement of air that drives the air masses from one place to another. The more dense air mass lifts a less dense air mass. And the result is a cooling, condensation, and leads to cloud formation, and then eventually precipitation. The extent of the cloud cover and precipitation depends on how much lifting occurs and the amount of moisture in the atmosphere.